Okay, so hello everybody, and today we are going to continue with our Chapter 3 notes. We're actually going to be looking at Section 3 in the book. We're going to start looking at motion along a curve, specifically projectile motion. Now, there are other types of motion along curves, for example, circular motion, but we're going to be looking at objects that are projected. That means the object itself is called a projectile. If you throw a ball up and out into the air, it is a projectile. A golf ball hit down the fairway is a projectile. An arrow shot towards a target is a projectile. A cannonball shot downrange is a projectile. Anything that is projected into the air so that it is in free fall the whole time is a projectile. Now, that may sound a little confusing. If it's in free fall, shouldn't it be falling towards the earth? But a cannonball goes up before it comes down. An arrow goes up before it comes down. A golf ball goes up before it comes down. You've got to remember, as long as we're neglecting air resistance, this means the only force acting on the object once it becomes a projectile is gravity. And in that case, it is in free fall. It doesn't matter which direction it's moving, up or down, it's in free fall. Now, this motion, projectile motion, exhibited by an object, the shape of the resulting path followed it by a projectile. Let's fill in these words. I don't know why I had this one blanked. It's a parabola. If you've ever seen if you've ever used a golf simulator, the shape of the path of the ball is a parabola. If you've ever looked at a football pass downfield, it's the shape of a parabola. All projectiles follow some part of a parabolic path. There's three that we will be considering in this class. The first is half parabola projectile motion. That means the object starts above where it ends, or it could start the other way. It could go up, but usually it starts above where it ends, and it has an initial horizontal velocity, and it follows a parabolic path down to the ground. In other words, it's half a parabola, starting at the top, at the vertex of the parabola, and coming down. A full symmetrical parabola sounds exactly like what it is. It's both sides of the parabola. It goes up to the top and then comes back down to the ground, like the golf ball. Then there are non-symmetrical parabolas. And if we look at non-symmetrical parabolas, that just means the vertical ending and beginning point are not the same. For example, if you kick a ball and it lands on top of a house, all right, it doesn't make it all the way back to the ground from whence it started. So that is a non-symmetrical parabola. There's an up part and a down part, but they're not mirror images of each other like they are in this full symmetrical parabola. Okay? We're going to start with the easiest, and that's the half parabolas. Okay? We're going to learn about the horizontal motion of the projectile and the vertical motion of the projectile. Remember, they are independent of each other, so we must treat them separately if we want to avoid using calculus. Also, please remember that in kinematics, there are four kinematics descriptors, four variables that we use to describe motion. Whoops, there we go, descriptors. Those four descriptors are displacement, velocity, and by velocity I'm including both initial and final, acceleration, and time, the one scalar. So we have three vectors and one scalar, okay? So these four descriptors are going to help us describe the motion in each plane. So let's take a look. Let's suppose that we're on top of a building and we are going to project an object horizontally, say a ball. Now, please remember, if we project it horizontally, when we throw it, we give it a horizontal velocity. That means the moment it leaves our hand, so that our force is no longer acting on it, it will have a horizontal velocity. And the only force acting on it once it leaves our hand is gravity. So it has become a projectile. So when we look at projectiles, we look at the point when it becomes a projectile, meaning only gravity is now acting on it, until it reaches the end point. Once it reaches the end point, it's no longer a projectile. So, for example, when this ball does eventually hit the ground will exert an upward force and change the motion of the ball. When that's happening, it's not a projectile then. So we don't look at that part of the motion. We look from the point it's released to the point it strikes the ground. That's it. That's the only time it's a projectile. Keep that in mind. All right, so if we throw it horizontally, then our object is going to follow a parabolic trajectory to the ground. Let's see if I can make these meet. Boom. Just like that. A nice half parabola where the ball starts at the vertex. Now we're going to look at both the vertical and the horizontal motion, okay? But in order to visually differentiate the two motions on our paper, I am going to color code it. I'm going to use blue for horizontal, or X direction, and I'm going to use green for vertical or Y plane motion, okay? Now, we're going to start with the horizontal motion of the object. As the ball travels outward, and we will look at specific points along through here. As the ball travels outward, what happens to that horizontal velocity with which it travels? Okay, we're going to look at some of these points right here. So just mark yourself a few points just like I did. Well, gravity is the only force acting on the object because we are neglecting air resistance. We're looking at an ideal situation in those terms, no air resistance. So the only force acting on the ball is gravity. Gravity is vertical. It pulls down. Now remember, vertical and horizontal vectors, x and y vectors, perpendicular vectors, are independent of each other. So does the gravity affect the horizontal motion of the ball? Absolutely not. It's independent of the horizontal motion you gave the ball. It can't change it. So as the ball travels outward, its horizontal velocity does not change. It stays the same magnitude, hence why I'm drawing these arrows the same size. In fact, as it strikes the ground, the horizontal velocity is just the same as it was at the beginning, okay? It's constant. In fact, what we could say right here is that the final x velocity equals the initial x velocity. If we want to put a little x on those to show that it's horizontal. It is the same. It hasn't changed because there's no horizontal force acting on it to change it. I like to say there are no angels in the outfield. If you've ever seen that movie, Angels in the Outfield, you know what I'm talking about. All right. So there it is. The motion is constant, okay? So let's actually talk about that right now. What happens to the projectile's horizontal velocity during the trip? The horizontal velocity, v sub x, remains constant, which means in the general equation, here's how we would describe it mathematically. D sub x equals v sub o x times t, and that stays constant. We don't need the 1/2 at squared part. So that's another piece of information. The horizontal acceleration, a sub x, is 0 for the entire trip. Now, here's something you need to understand. We know if the velocity is constant in the horizontal plane, the acceleration is 0. Are they ever going to remind you of that in a problem? No, they're not. So this is one of those understood or inferred pieces of information you're going to need to be aware of for the horizontal motion of a projectile. So we put a little star beside it so we remember that. Okay. Now, let's talk about how far the object travels. Well, the ball started here, it was released right here, and it traveled all the way out to here. So we call this distance traveled. If you wish, you can say xf for the final position if you want, x sub f, and knowing that the initial position is 0. You could also say, oh, xf minus x sub o, that would be d sub x, the horizontal distance traveled. But one thing you do need to know about this, it is also got a name. It's called range, and you need to know that. The horizontal distance traveled by any projectile is called the range. If you've ever heard mention of a missile being fired downrange, that means the horizontal displacement of the missile. Okay. Now, so we have the initial horizontal velocity stays constant. We have the horizontal acceleration is 0. And we have the horizontal distance traveled is the range. And of course, we know this takes place in a time we'll call t sub x, the time for the horizontal part of the motion. Okay, now let's talk for a minute about the vertical motion. So I'm going to switch colors. I'm going to use green for vertical. All right? The first thing that we need to understand is that objects can go up as well as down. If they're projectiles, they only travel one direction horizontally, so you can always make that positive. Projectiles, on the other hand, can travel up and they can travel downward. That means we need to decide what we want to do. Do we want up to be positive and down to be negative, or do we want the reverse to be true? It really doesn't matter which way you look at it, as long as all the vertical vectors in that problem have the appropriate sign for what you choose for your convention. Okay? Now, for a half parabola, it starts at the top and comes down. It never goes up. So for this particular problem, we could say down is positive. However, for purposes of graphing in a little while so that you see how all the graphs relate, I'm actually going to let down be negative and up be positive. Okay? Because this will actually correspond to what we do in the other two situations, and I don't want to freak people out, so we're going to use the same sign convention for this one as we do for the other two, if that's all right with you guys. Okay. Now, so understanding our sign convention, let's take a look at what the ball does vertically. First off, when you release it, the moment you release it, it's only traveling horizontally. Then gravity begins to accelerate it downward immediately when you let go of it. So it has to start accelerating downward. That means that the initial vertical velocity has to be 0. If it has to start moving, it starts from 0. Now, are they ever going to tell you this in a problem where something is projected horizontally? No, they're not. This is another one of those inferred pieces of information. In fact, right down here, we probably need to put a little thing and identify what we're talking about, okay? So I'm going to say inferred info, so that later when you see those, you'll know what it means. All right, so it starts from rest, it begins to accelerate downward. Now, we know that all objects in free fall have an acceleration that is caused by the force of gravity. And that acceleration always points down, and we said down is negative. So we're going to say negative 9.8 meters per second squared. Okay? And are they ever going to tell you, oh, by the way, don't forget it's in free fall, so use the acceleration due to gravity? Of course they're not. As a physics student, especially an AP physics student, they're going to expect you to understand that the motion in the vertical plane is free fall. So, there we go. Let's put a little star beside that one. Now, for this type of problem, those are the only 3 inferred pieces of information you will have. So, that's not too bad, just 3 things. And I think we can remember that. All right, so let's continue. As it starts from rest and accelerates down, that means as it's traveling, the vertical velocity gets bigger and bigger and bigger. Okay? And then when it strikes the ground, it will have some final velocity in the y-plane. Okay? Also, it will travel downward until it vertically. It's like somebody just drops it, and it just starts from rest and accelerates down due to gravity and hits the ground. It's going to cover this vertical distance right here. And we can call it d sub y, or if you want to take this to be x sub f, and this x sub o, you would get 0 minus whatever's at the top, so you get a negative displacement. And if you want, you could just say d sub y. You could also just say x, since one of these is 0. So what do we name this vertical displacement that it goes through? Well, if you remember, anytime you go down like this, you drop from a height. That was easy enough. That's a word you know. H-E-I-G-H-T, a height. So we have the range in the horizontal plane, we have the height in the vertical plane. Okay? Now, we've only looked at 3 of these. Let's talk about the time it takes to fall. Now I want you to remember there's only one ball. And as it's traveling this curved path, the reason the path is curved is because of this vertical velocity. If you look, the resultant, if you put these 2 tip to tail, the resultant is going to get bigger and bigger, and it's also going to change direction because of the changing vertical velocity. It's going to change so that it points more and more downward as it travels. Okay? So, when we get to the end, the vector sum of the vertical velocity and the horizontal velocity, if I put them tip to tail, I'm just going to slide this one over so it's right there, then we get a resultant velocity that is the vector sum of those 2. In fact, if you know these 2 right here, the horizontal and the vertical, you can determine the angle at which it strikes the ground. That's kind of cool, isn't it? So let's write some formulas that we know would work for this. VF, all right? So VF, in this case, if you can use kinematics to find the horizontal motion and the vertical motion, then the actual resultant final velocity would be the vector sum of the x component squared plus the y component of the final velocity squared. Just take those 2 components, square them, add them, take the square root. In other words, Pythagorean theorem. If you want to find the angle, then you can do what we've done in vector addition already. You can just say, oh, well, we found the legs, so if we want the angle, we can say the inverse tangent of the opposite leg, which is vertical, over the adjacent leg, which is the horizontal, and it would be directed below the horizontal or below the x-axis. Okay? Because remember, we always reference from the horizontal. We always measure from the horizontal up or the horizontal down. Okay? All right. Now, the time. Let's talk about that again, real quick, because I think I skipped it a minute ago. We have an object that starts from rest, accelerates downward, accelerating due to gravity with this, from this height. And it does it in amount of time ty. But both of these motions, the ball doesn't travel outward and then downward, does it? Both of these motions are taking place concurrently. And if you don't know what that word means, you need to write it down. Concurrent. Now, what does that mean? That means at the same time. Okay? Concurrent means at the same time. So what does that tell us about the time it takes for the horizontal motion and the time it takes for the vertical motion? They're the same. So that means the time can be used for either motion. Remember, time is a scalar and it is independent of anything else. So it can be used to help you describe both the horizontal motion or the vertical motion. If you have a cannonball that's shot down range and it takes it 30 seconds to hit its target, during that 30 seconds, it traveled up and down and it traveled out, all at the same time. So we can use the time for both motions, and that's just fine. All right, now let's continue to answer some of these questions. We said that the horizontal motion is constant, but what about the vertical velocity? All right, the vertical velocity, the velocity in the y-plane, increases in what direction? Downward. And it does so uniformly. In other words, it's always by increments of 9.8, never any other increment. Okay? Acceleration due to gravity is a uniform acceleration. The increments are always 9.8. Now, let's write out our descriptions of the motion. Okay? In fact, wait, before we do that, before we do the English description, let's do the math for this one. Here's the math for the horizontal motion. Let's look at the math for the vertical. For the vertical motion, since we're using our 4 variables up here, our descriptors, this is the general equation. Let's start with that one here too. D sub y equals v sub o y t, but this changes because we have an acceleration. So we have to have the 1/2 ay t squared part. Now, if you wish, you can, oops, I just realized. Okay. You can use little g to represent the acceleration due to gravity right here. You don't have to if it confuses you. You can just say ay, it's your choice. A lot of times I'll just write 1/2 gt squared. When you see that, you should understand that we're talking about an object accelerating due to gravity. So this is how we will describe the motion mathematically in the horizontal plane, and this is how we will do it in the vertical plane. Okay? And in fact, even though this looks difficult, you got to remember it starts from rest. That part will drop out in this situation, a half parabola. It starts from rest, so you really only need these 2 parts. That's kind of nice, isn't it? All right, let's do the English description. When we talk about the ball's motion horizontally, let's think about how it starts out. It's a projectile. It's a projectile at the moment you release it, so that the only force acting on it is gravity. Now let's describe the motion. All right, we know it has an initial horizontal velocity. Okay, so let's write that. The projectile, whatever it is, the golf ball, the football, the cannonball, whatever, the missile, the projectile has an, whoops, okay, I started to put two things together there. An initial horizontal velocity, and what happens to it? Which remains constant. So there you go. There's the English description. That's how you would say it in English. The projectile has an initial horizontal velocity which remains constant. Okay, now what if you were asked to describe the vertical motion? They do ask this stuff on the AP exam quite often. They want to see if you can write it as well as do it mathematically. In fact, there'll be very little math. It's mostly going to be writing, so we have to get good at this. So here we go. Vertically, we know it starts from rest. So let's say that. The projectile starts from rest. Okay, what does it do when it starts from rest? It accelerates down uniformly. Starts from rest and accelerates down uniformly. Now, do we have to say due to gravity or because of gravity? No. Gravity is a force. It's not a kinematics quantity. Forces explain. We're not doing that. We're describing. When you're describing the motion, you don't talk about the forces, okay? You talk about the motion, the velocity, and what's happening to it. But you don't talk about forces. So that's why we don't have to tack that on at the end. We just say it starts from rest and accelerates down uniformly. All right, let's look at this example real quick. A ball rolls across a lab table with a speed of 0.88 meters per second. It rolls right off the table, boom, and hits the floor located 0.85 meters below the top edge of the table. How far from the base of the table does the ball hit the floor? Now, here's where I'm going to teach you how to look at this in a way that will help you keep everything separate. Remember, the two motions that we're talking about have to be worked separately. They're independent of each other. They're very different. So here's what we do. Watch this. You guys are going to like this. This is pretty cool, okay? We're going to create what I call a DVAT chart. What in the world is a DVAT chart? Well, one side is going to be for the horizontal motion, and the other side is going to be for the vertical motion. We split it in half and split each half in half. Okay, just like this. And down the side, we put a D, a V sub O, an A, and a T. Now, later on, in some of them, we might also do this. We might add a fifth row and put a V sub F if we're asked to find that. For now, we probably don't need it, I think, because I don't think that will have any bearing on how we can get the answer for what they want here. Now, once you have your DVAT chart created, the first thing you do before you even start looking in the problem for stuff, the first thing you do is you come back up here and you say, oh, I had 3 pieces of inferred information for this half parabola problem. Let's put them in the chart. So let's start with the horizontal side. Oh, the acceleration is 0. So we come down here, okay, and on the horizontal side, we put 0 for the acceleration because it's inferred since it's a half parabola, okay? Now, come back up here. We have 2 vertical inferred pieces of information. The initial velocity is 0, starts from rest, and it accelerates down due to gravity, and we're making down negative. So here we go. The initial vertical velocity is 0, and the acceleration is negative 9.8 meters per second squared. Both of those are inferred. So now, look, we've got 3 things fitted in already. Now let's get the information from the problem. Look at what it says. The ball rolls across a table. Now, what do you know about a tabletop? It's horizontal. So what does that make this speed? That's the speed at which it's moving horizontally when it leaves the table. So it goes on the horizontal side, 0.88 meters per second. Okay? It says it rolls off the table and it hits the floor, which is located 0.85 meters below the top edge of the table. What does below mean? It means down. So this is the vertical displacement from the edge of the table to the floor. So we're going to put this right here, 0.85 meters. Okay? Now, oh, I just realized I put that in the wrong spot, didn't I? Boy, that was real smart. That was really smart, guys. Hang on, let me get my white out. And how many of you are sitting there thinking, oh, Miss Pepitone, what are you doing to us here? What are you doing? Well, one of you could have mentioned it to me, except, well, this is a video and you can't. So there you go. All right, so 0.88 meters per second. There you go. Now we've got it right. See, it does help if you identify things properly, doesn't it? All right, so now we've gotten that taken care of. Now let's look at this. What are we trying to find? How far from the base of the table, the bottom of the table? So if we looked at a little side view of the table, and here's the ball, what are they asking for? They're asking for this. They're asking for the range. Okay? They're asking for the range. So we want to know, what is that? All right? Okay, now, how are we going to figure it out? Because notice, we don't have enough information. And we're not going to need to worry about this. We don't have enough information here. We've got 2 knowns, 2 unknowns. You have to have, for this right here, to use this, you have to have at least 2 of the 3 to solve the problem, right? But we don't know the distance or the time. What can we do? Well, nothing with the horizontal side yet. So let's look at the vertical side a minute. We've got D, V sub O, and A. So let's go up here. We have D, V sub O, which we know is 0, and A. Oh, look! We've got 3 of the 4. We can use the vertical motion to find the time. And since it's the same time for the horizontal motion, we can move it over and use it on this side and get the horizontal distance, the range. Okay, let's do that. Let's start with the vertical side. Okay, we're going to say dy equals 1/2 ay t squared, or if you want to say g, you can. Notice I didn't put in the v sub oy part. Why? Because it's 0, and 0 times t is 0. So we get 0.85 meters equals 1/2